In the second part of this section, I'm going to talk about the method of Lagrange multipliers in order to solve convex optimization problems. So we consider the problem minimize f of x subject to gi of x is less than or equal to 0 for all I from 1 to m, and also x is in omega, where f is a function from Rn to R, and gi are functions from Rn to R, and we assume that they are convex. And omega is a non-empty convex subset of Rn. Okay, and we denote this problem by P. Okay, so let me first give some definition related to this problem. So we say that an element x bar in Rn is a feasible solution of P if the following condition is satisfied: if x bar is an element of omega and gi of x bar is less than or equal to 0 for all I from 1 to m. That means x bar satisfies the constraint of the problem. So this is so x bar is a feasible solution of P if x bar is in omega and gi of x bar is less than or equal to 0 for all I from 1 to m. Okay, and for x bar in Rn, we also define the set of active indices associated with problem P by A of x bar. This is the set of all I from 1 to m such that gi of x bar is equal to 0. Okay, so that means the equality is satisfied for such an I. Okay, so let me introduce the first theorem that is important for what follows. Consider problem P. So here we suppose that x bar in Rn is an optimal solution of P. Okay, what does it mean? It means that x bar satisfies the constraint here, and for any x that satisfies this constraint, f of x bar is less than or equal to f of x. Okay, so under this condition, then there exists multipliers lambda naught, lambda 1, so on lambda m, not 0 simultaneously. Such that 0 belongs to the sum of, such that 0 belongs to the lambda naught times the subdifferential of f at x bar plus the sum of lambda I times the subdifferential of gi at x bar, where I runs from 1 to m, plus the normal cone to the constraint set omega at x bar. And over here, lambda naught, lambda 1 up to lambda m are all non-negative. And at the same time, lambda I times gi of x bar is equal to 0 for all I from 1 to m. Okay. So this condition is called the complementarity condition. And this condition means that if for some multiplier here, if the multiplier is positive, then gi of x bar is equal to 0. That means I belongs to the active index set associated with this problem. Now I'm going to go through the detailed proof of the theorem. Okay, so let x bar be an optimal solution of P. Okay, again, it means that x bar satisfies the constraint and f of x bar is less than or equal to f of x for any x that is a feasible solution. Okay, then we define the function phi from Rn to R by this formula. Phi of x is the max of f of x minus f of x bar, and gi of x, where I runs from 1 to m, and x here is in Rn. So because phi is the maximum of a finite number of convex functions, phi is also a convex function. Observe that phi of x bar is equal to 0. And how come this is true? Because when you plug x bar in here, f of x bar minus f of x bar, so it is 0. And at the same time, because phi x bar satisfies the constraint, so gi of x bar is always less than or equal to 0. Therefore, the max is equal to 0. And x bar is an optimal solution of the problem in which we minimize the function phi of x subject to x in omega. Okay, so we can really check this by showing that whenever x is in omega, we see that phi of x is greater than or equal to 0, which is phi of x bar. Okay, so we can really check this by showing that phi of x bar is less than or equal to phi of x, and this is true for all x in omega. Okay, I'm going to give a hint to check this. Okay. So we actually consider two cases for x. Okay, we fix any x in omega, and we consider two cases. Now, if gi of x is less than or equal to 0 for all I from 1 to m, then x is a feasible solution of problem P. Therefore, f of x bar is less than or equal to f of x. And so, f of x minus f of x bar is greater than or equal to 0. In that case, phi of x is greater than or equal to 0. That is phi of x bar. Okay. Now, in the second case, where there exists some I from 1 to m, so that gi of x bar is greater than 0, then this max is greater than 0, which is also phi of x bar. So in any case, this is always true. Therefore, x bar is an optimal solution of this problem. Okay. Now, by the optimality condition, presented in the previous lecture, we see that 0 belongs to the subdifferential of the function 5 at x bar plus the normal cone to the constraint z omega at x bar. Okay. To proceed, we are going to express the subdifferential of the function 5 at x bar in terms of the subdifferential of the function f at x bar and the subdifferentials of the function gi at x bar. And here, phi is the maximum of a finite number of convex functions. We already have such a formula for computing the subdifferential of the function 5. Okay, so to do so, we define g naught of x by this formula, by f of x minus f of x bar. Here x is in Rn. Then phi of x is the max of gi of x, where I runs from 0 to m. Okay. So associated with this maximum function, we have the active index set I of x bar given by the set of all I from 0 to m, such that the maximum here is attained. That means gi of x bar is equal to 5 of x bar and is equal to 0. This set is required for computing the subdifferential of this maximum function, and we can refer this to my lecture on computing the subdifferential of the maximum function. Okay, so then as we see, for if I is equal to 0, then g naught of x bar is f of x bar minus f of x bar is equal to 0. That means g naught of x bar is always 0. Okay, and we also see that gi of x bar is also 0 if I is in the set A of x bar, because if I is in the set of A of x bar, then gi of x bar is 0 by its definition. Okay, so the set I of x bar here is just 0 and union with A of x bar. Okay, so by the subdifferential formula, for the maximum function, zero is in the convex Hall of this of the subdifferential of T naught at x bar and union with the union of the subdifferential of Gi of x bar, where I runs in A of x bar. This is the subdifferential of the function 5. And we add the normal cone to the set omega at x bar. Okay? Now, because T naught of x is f of x minus a constant, the subdifferential of T naught at x bar is equal to the subdifferential of the function f at x bar. So this is equal to the convex Hall of the subdifferential of f at x bar, and then we take the union with the union of the subdifferential of Gi of x, where I runs in A of x bar, plus the normal cone to the set omega at x bar. Okay? So therefore 0 can be written as the sum of a convex combinations of sets in these subdifferentials and an element of the normal cone to the set omega at x bar. So then there exists lambda naught greater than or equal to 0 and lambda I greater than or equal to 0 for I in the set A of x bar with this property, the sum of lambda naught and lambda I, where I runs in A of x bar, is always 1, and 0 is in lambda naught times the subdifferential of f at x bar plus the sum of lambda I times the subdifferential of Gi at x bar, where I runs in A of x bar, plus the normal cone to the set omega at x bar. Okay? Now, to make this sum nicer, we're going to set lambda I be 0 if I is not in A of x bar and I is from 1 to m. Then from here, because when we add 0, the sum doesn't change. So 0 belongs to lambda naught times the subdifferential of f at x bar plus the sum of lambda I times the subdifferential of Gi of x bar, where I runs from 1 to m, plus the normal cone to the set omega at x bar, where we also observe that the complementarity condition is satisfied. That is, lambda I Gi of x bar is equal to 0 for all I from 1 to m. Okay, this is true because of the following reason. If I is not in A of x bar, then lambda I is 0, so this is 0. Now, if I is in A of x bar, then Gi of x bar is 0, so the product is also 0. Okay, so we have found multipliers lambda I for I runs from 1 to m that are not 0 simultaneously because of this condition, and at the same time this inclusion is satisfied and the complementarity condition is also satisfied, and therefore the proof of the theorem is complete. In many applications, we need conditions in order to guarantee that lambda naught is not equal to 0 in this inclusion, and therefore by dividing both sides by lambda naught, we can guarantee that lambda naught is equal to 1. We can assume that lambda naught is equal to 1. And let me introduce a very well-known condition in convex optimization called the Slater's condition. Okay. We say that the Slater's condition is satisfied for problem P if there exists u in omega such that gi of u is strictly less than 0 for all I from 1 to m. Okay, that means there exists a feasible solution u such that these inequalities are strict. That means gi of u is strictly less than 0 for all I from 1 to m. Under that condition, under the Slater's condition, we can show that lambda naught is not 0, and therefore we can assume that lambda naught is 1 by again dividing both sides by lambda naught, and that is the content of the next theorem. Okay. Now consider problem P. Let x bar be a feasible solution of P. Now we suppose that the Slater's condition is satisfied for P. Then x bar is an optimal solution of P if and only if there exists multiplier lambda 1 up to lambda m all greater than or equal to 0 such that 0 belongs to the subdifferential of f at x bar plus the sum of lambda I times the subdifferential of gi of x bar, where I runs from 1 to m plus the normal cone to the set omega at x bar. And again, the complementarity condition is satisfied. Okay, so there are two differences in this theorem. First of all, this is a necessary and sufficient condition, and at the same time, we can assume that lambda naught is equal to 1 in this inclusion. So this theorem is very important in the sense that in order to solve this optimization problem, we only need to solve this inclusion under the complementarity condition. And in many situations, for example, when the functions involved are differentiable and omega, for example, is the whole space, then this is just 0, and then this is just an equation, and we can solve an equation in order to solve a convex optimization problem of this form. Okay.